We continue with the encoder-decoder paradigms for node embeddings. Now, the previous manifestations of this idea basically used very simple functions to define the proximity between nodes, either edges or the weights of edges. What about longer path, right? Richer relationships. And here we look about this idea in the context of random walks or using random walks for this idea. And it comes from the idea, the algorithm of word2vec. This was a very successful embedding model for natural language processing and was the motivation of many techniques and many models that evolved from it. Okay, so what is the idea of a word2vec? You train it on a corpus of documents. So you have a collection of text documents, and you have sliding windows running over these text documents. Now, what your task is basically to predict words in these sliding windows. Okay, and to have a good prediction of what the words are in these sliding windows, well, you mask them, okay, in order to produce the tasks. But you use the embeddings as the parameters of your prediction model. So the predictions should be good and should capture the semantics of words in order to allow you to guess the words properly. Okay, and there are two main variants of that. In CBOW, the continuous bag of words, you guess a word from the context, and the complement approach is skipgram, where you guess the context words from a word, from the center of the context. Okay? And in that work, they also introduced the idea of negative sampling that we've seen in the previous part. Okay? Now, this is an illustration of a CBOW and skipgram, an example. So you see here apples ate something and apples are something and juicy, and you want to predict, okay, the missing word is sweet. Apples are sweet and juicy. Or you say sweet, what is the sentence around it? That's a skipgram. Okay? And what you get in the end using skipgram is the following. You have your text and you have your running window going through the text. And these running windows basically produce tasks which are pairs, simply pairs of words. And you want to predict one word from the other. That's all. This is what you're getting from the skipgram model. Very simple conceptually, right? Now, how is it related to graphs? In text, we have words. What do we have on graphs? Well, in graphs, we can use random walks. A random walk is basically a walk that you establish by choosing the next step, the neighbor randomly. You start with a source node, and then you choose randomly, is it this neighbor or that neighbor? You choose randomly the next neighbor, and then the next neighbor, and so on until some number of steps. So you produce a path, a random path, okay? And the adaptation from text to graphs is the following. You treat the nodes as your words, and instead of sentences, you have random walks. So these random walks are basically your sentences, and you have a collection C, that's your corpus of documents, right? These random walks, and you learn the embeddings from this corpus. And it turns out that skipgram is the more popular alternative, more popular than CBOW. Okay, now this is how it looks like. Go in an illustration. So you have the graph. You produce random walks. These are our sentences. And we have, okay, so in each sentence, each node is a word. We have the running window over the sentences. What else? And then we mask, right? We mask parts of the window, trying to guess what it is. Okay, so this is the idea. So here's one instantiation of this idea, deep walk, where basically the proximity is the probability of visiting U. Okay, so you need to define the proximity between U and V. So it is the probability of visiting U in a path that includes V. Okay, the probability of seeing U in the context of V. And you do it empirically through these sentences that you produce using the random walks. Okay, and so the coding function also tries to predict U from V. So the idea is that you use the parameters, the embeddings, the embeddings are the parameters of a learned regression model that aims to compute this probability of U given a Z. And how do they do that? It's an interesting technique. We won't get to the details of that, but just get the general idea. They use the concept of a hierarchical softmax, where they basically say, let us put all of the nodes in a tree, in a balanced tree. And then, given context word V, we will try to guess where U is in this tree. Okay? And basically, we will try to match this probability with the proximity. We will see how they do that. But basically, what do you need to do? If you have all your nodes in a tree, then you need to make, and it is balanced, then you need to make log V choices of where U is. What is the first, because it's a binary tree. What is the first step? What is the second step? Log V choices. Okay, so basically, what I say is, okay, let's treat it as essentially log V classifiers. Okay, and then the probability of visiting U given the embedding of V is the product of the different steps given ZV. That's the model. Okay, what is it gaining? It encourages nodes that have the same neighborhood to have similar classifiers, similar these probabilities, BIU given ZV. Since they have similar classifiers, they're encouraged to have similar coefficients. Okay, like think of a linear classifier. And therefore, nearby embeddings, because these embeddings are essentially these classifiers. Okay. So the learning technique is the usual one, okay, adapted to our random walks. You go over walks, well, look at the walks that include V in some random order, and whenever you see a node U, you apply this probability. You apply SGD to update this probability. You say, okay, I now want to increase the probability of seeing U given that I started with V. Okay, that's the idea. This is the pseudocode, and you can see in the pseudocode, well, here they build this binary tree representation, and then they go through the nodes. For each node, they create set of nodes, basically a set of context random walks from this node. And then they apply the escape round. In the escape round, they say, okay, let's look at the random walks or the nodes of the random walks. And for each one, for each node U that we encounter, we apply a gradient descent step. Okay, we have the probability of UK given the embedding of VJ, and we compute the gradient and apply an SGD step. Okay, so this is the idea. And this is a nice illustration or a case study that they do on the karate network, where they say, well, we started with a graph, and these nodes have different types corresponding to colors. And when we embed and apply thisness, see what we are getting, okay, from that. And the 2D representation, has quite a similarity to the original semantic representation. Another algorithm is node2vec, okay? And this is similar to deep-walk, but I guess with a more direct probability expression. This decoder, DUV, is basically dot product, normalized dot product. So it's the exponent of the embeddings, of the dot product of the embeddings, normalized. Normalized by W. UV, you normalize it by UW. But generally, it is the same idea. And then if you want to normalize and you want to do it efficiently, what do? Negative sampling, right? Right one, negative sampling. Something special about that is that they enrich their random walks with different probabilities. The probability of going in one direction of the edge, or they have these three hyperparameters going back in the edge, staying at place, or moving to a new node, right? Taking a through a random step. Okay, and then these are hyperparameters that they optimize to get good results um, on a collection of training data. Okay, so that's another improvement of Node2Vec. Okay, and you can see experiments from Node2Vec, similarly to things that we've seen already. They look at multi-class classification, they apply logistic regression over the embeddings. Okay, so they train over the embeddings and test over the embeddings and use different portions of the training data to see how effectively they learn. And they compare it to deep work and, the line that we've seen previously. Okay. Another well, it's a good opportunity to remind you of the use case of node embeddings for whole graphs. Okay, and this is something that also is also applicable to text. For example, you have doc2vec. Okay, so in graphs we have a graph2vec, and the idea is kind of a generalization of what we've seen. So we have learn embeddings ZV, and also we have graph embeddings ZG. So we have many graphs, and if in each graph we have embeddings of nodes. And now for each node, we list neighbors in the neighbors or nodes in the neighborhood of V. And then we are trying to predict this neighborhood. And we do so basically by using the embedding of the graph ZG as part of the parameters of our model. So it is ZG times ZV multiplied over all of the neighborhoods. So that's the probability of the neighborhood. And then you normalize it with other neighborhoods. And for that, again, negative sampling is used because, as you can imagine, there are many neighborhoods. Okay, that was it. Next, we're going to look at another instantiation of the encoder-decoder paradigm using linear algebra.